Hello, this is a worksheet to help you review for chapter 9. So hopefully you've already worked on the problems and you're going to use this to help you check and verify and get a better understanding of the concepts. So question 1 says, a researcher carried out different two-tailed hypothesis tests. Which of the studies is associated with the smallest p-value? So remember that a p-value is the likelihood of an event happening in the tails. So the further you get away from the center, the least likely it should happen. And the further you get away from your center, the further away or the bigger as an absolute value your z-scores are going to be. So think of it like this: z-score, the absolute value of the z-score, if it gets bigger, then your p-value, the likelihood, is going to go down. So the one that is the smallest p-value is going to have the furthest away from the center, and that would be study A. It has an absolute value of 2.5 standard deviations. Which of the studies is associated with the largest p-value? That would be the one that has the smallest z-score, and that would be study C. So question 2 says, pairs of p-values and significance levels alpha are given. For each, determine whether the observed p-value leads to rejection of H0 at the given value. So we reject if the p-value is less than alpha. So this would be no. This would be no. It's not a less than, it's equal to. This would be yes, and this would be yes. Which study has the lowest chance of a type 1 error? So a type 1 error is rejecting H0 when H0 is true. So that would be the lowest alpha, which would be study B. The lowest type 1 error. C says, which study has the lowest chance of a type 2 error? Well, they're not. Alpha and beta aren't exactly complements, but they are related. So I would say the one that has the highest alpha would probably have the lowest beta. So that would be C. Which study has the most statistically significant p-value? That would be the smallest p-value, which would be letter D, 0.001. Which studies had statistically significant results? So statistically significant is equivalent with rejecting H0. So that was studies C and D. F says, we do not know if any of these studies had results that were practically significant. Explain why not. And that's because we don't know all of the details of the context. Remember that practical significance is different than statistical significance. Practical significance has to do with if I'm making a plastic part, like this plastic little cup here, right? If there's something not right about it, it's not as big of a deal than if I'm testing the significance of a cancer drug. So that's practical significance. Question 3 says, a medical journal states that the p-value is less than 0.0001. Why do we not have an actual number? Okay, and that's because p-value is so small but they would have to write it in scientific notation. It's so small. And then it says, is that p-value statistically significant at alpha 0.01? And that's a resounding yes, because anything that's less than 0.0001 is definitely less than the alpha of 0.01. Remember that statistical significance is the same as rejecting H0, and we always reject H0 if our p-value is less than the alpha. Okay, question 4. So the manufacturer is designing a new jet engine, part of that is critical for keeping the engine going and the plane up in the air. The manufacturer is testing the part for strength and comparing it to the older traditional part they used to use. If the new part is stronger than the old one traditionally used, the manufacturer will place it in the new jet engines. Describe the types of possible outcomes in the grid below. Label the errors as either false positives or false negatives. Okay. So the H0 is the new part is not stronger, and H1 is new part is stronger. The decision is what they're testing from. The actual situation is in real life. Okay. And this is the testing results. So this box right here is H0 is true. Part is not stronger. And test results agree. Don't want to use the new part. Here, it's reject H0, so new part stronger. But in reality, it's not stronger. So testing says new part stronger, but it actually is not. This is a type 1 error. And this is what we would call a false positive. Okay. So here they would be using the new part, even though it's not stronger. That could cause an accident, right? Okay. Let's go over here. Over here, it says that we claim the testing says the new part is not stronger, and it really is. It really is. This is a type 2 error. This is a false negative. And then the fourth outcome is the new part is, the testing says new part is stronger. Is stronger, and it really is. And this is, these two are both correct. Part is not stronger, and it really isn't. part is stronger, and it really is. So not is. These are both correct statements. Good outcomes, I should say. Okay. So it says, B says, which is worse in this case? And I would say they've been using the old part, and it doesn't say it's been causing crashes. And so if you have something that's stronger, that's amazing, even if you actually said it wasn't. But I think the type 1 in this case is a worst case scenario, because you might be using a part that could cause accidents. Could start using a new part that is not stronger and could cause an accident. And we don't want that to happen. Okay. So remember that this is always in reality, the actual situation. And then over here on the left is always the testing results. And remember, when they do testing, whether it's pharmaceutical, whether it's in automotive, whether it's testing the chemicals on our cornflakes that, that they put in their preservatives, whatever it is, it doesn't always mean that the testing is good and true, because there could be things wrong with the manufacturing. So there could always be a difference between in real life and what our testing says. Okay, let's look at example 5. Question 5 says, in June of 2020, Johns Hopkins researchers released a study stating that in the US, there was about 38% false negative rate for COVID-19 tests. Now, remember, this was only a few months after supposedly COVID showed up in the US, and things were still a hot mess here. So it says, what does it mean for the COVID-19 test to give a false negative? So that means test says person does not have COVID, but they really do. Now, there's kind of two big things that could happen here. One is they are unknowingly, because if they don't think they have COVID, they're walking around spreading it. They are unknowingly spreading the disease. And 2, if they're actually sick, they have symptoms and they're feeling sick, but it says they don't have it, they aren't getting medical treatment that they should. Aren't receiving medical treatment that they need. Okay. Let's look at question 6. Question 6 is one big hypothesis test. So let's read through this. It says, conventional wisdom says that the average movie length is 2 hours, but you think this is not true. To check your claims, you gather a random sample of 33 movies from IMDb and find their average length is about 109.39 minutes with a standard deviation of 17.25 minutes. Okay. Are the requirements for conducting a hypothesis test satisfied? So we first have to decide, is this qualitative or quantitative? And they use the word average, and we have units. So that is telling us that we're dealing with quantitative, something we're measuring. And average is telling us that we're talking about mean. Okay. So your page in your formula packet would be page 302. And so that would remind us that we're going to be using the t-distribution. Just some things that this should kind of be making us think about. So the 3 requirements, the first one is, did we take a random sample? And right there, they told us that they did take a random sample, so we can give that a check. The next thing is, we're checking for independence, because if we ask a person, or if we look at a movie and we measure how long it is, then we can't measure that again. So we can't sample with replacement. So because we have to sample without replacement, we have to check this independence. So we have to check to see if our sample is less than 5% of the population size. And our sample is 33 movies. And yes, that's definitely less than 5% of, it says there's 6.5 million movies out there. So yes, I would definitely say. So this is what you need to show me, the numbers, okay, and explain why. And then the third thing that we're testing for is to check to make sure our distribution is normal. And if our sample size, which is 33, is bigger than 30, then yes, we can say our sample is normal. Or they could tell us that it's a normal distribution, but we don't know that here. Or we could be given a normal probability plot. But we don't need the normal probability plot, because we have a sample size that's bigger than 30. Okay. Part B is asking us to test our claim at 5% level of significance, showing all steps working graph. We're gathering all the information from up here. So our hypothesis, because it's means, we're using the mu symbol. H0 always has an equal. And the number that we're comparing is always the same in our hypothesis statement. And it's what they think has been true. So they've always thought conventional wisdom says that movie length is about 2 hours. So we're going to put 2 hours. That's also the same as 120 minutes. Because the information they give us from the sample is in minutes. And they're claiming to check your claims, but you think this is not true. So we don't think that it's particularly less than 2 or more than 2. We just don't think it equals 2 any longer in the real world. So we're going to do a two-tailed not equal to 2 hours. The alpha that we want to test at is a 5% level of significance, so 0.05. And then our test statistic is a T0, and that's equal to our sample mean minus the population mean 0 divided by the sample standard deviation divided by the square root of n. So we have 109.39 minus 120. Remember, it's now in minutes. All over 17.25 divided by the square root of 33. I'm going to get my picture set up ready. And then I'm going to show you both the classical and the p-value methods so that you can see how both work. And then, of course, we're always going to write our conclusion. So because it's a not equal to, we have space on both sides over here. And we're going to go to Desmos. And we're going to calculate our U0. So I'm going to share my screen here so we can go to Desmos. We're going to go to means. This is means. So I'm going to put in my sample is 33. My sample mean, remember it says sample mean is 109.39. Standard deviation is 17.25. The mean for H0 is 120. So my critical T value is a negative because it's less than the mu 0. So negative 3.533. And my alpha level is 0.05. And then I'm going all the way down here and I'm choosing this one right here that says equal to with the exclamation point. That means we're testing the equality, but not equal to. And then our p-value is 0.0013. 0.0013. So again, I'm using the Desmos link that says confidence intervals on hypothesis testing for one sample mean. And this is what we're entering into that Desmos link. So going back to our paper to validate and finish this up, I am, because it's a not equal to, I'm going to page 302 and I'm going to look at my two-tailed test. And it says, I'm going to reject H0 if either the T0 is less than a negative T alpha divided by 2 or the T0 is greater than T alpha divided by 2. And we have to do alpha divided by 2 because it's a two-tailed test. So that means alpha divided by 2 is 0.025. So T of 0.025, comma, my degrees of freedom are 32 because my sample size is 33 and our degrees of freedom is n minus 1. So we can go to our formula sheet here, and we can go to 0.025. So 0.025 right here, and we're going to go down to 32. So that would be 2.037. Now, we only use the critical T if we're using the classical method. Okay, we only need that for the classical. So we're basically looking at this danger zone of a negative 2.037 and a positive 2.037. So our test statistic, the negative T0, so negative 3.533 is definitely less than and it's in the danger zone. Okay, so this is definitely out here somewhere. So it's definitely less than the negative 2.037. So we do reject H0. Now, if the alpha that you were using is not on the formula sheet, then we would have to use, I'm just going to show you as a reminder, in Desmos, the one that says critical Z and T scores. So because we're doing a T score, we're going to go right here. My degrees of freedom is 32, and the area that I want to find is 0.025, and it's going to be a negative 2.037 when I round. Now, remember, it's symmetric, so that's why we use a positive and a negative. Okay? Let's go back to our paper so we can wrap this up. Oh, and our p-value was 0.0013. That's also less than our alpha. So remember, p-value is compared to alpha if you're going to go that route. And classical method means your T0 is compared to your T of alpha divided by 2 when it's a two-tailed. So either way, either method, classical or p-value, will always give the same result. So in this case, we do reject H0. So our conclusion is there is sufficient evidence to support the idea that movies are no longer 2 hours long. We don't know how long they are, but we do have evidence to say that they're not 2 hours long. They're either less than that or more than that on average. And that is our hypothesis test for question number 6. Okay, the last problem we're going to look at for this review of chapter 9 is question number 7. It says, in 2018, an article for CNN stated less than a third of Americans own a gun. A researcher for the Pew Research Center decided to research this. They conducted a survey of 3,930 random adult Americans and found that 30% reported owning a gun. Okay, so it says state the null and alternative hypotheses. So let's kind of go through this. Less than a third is a couple things. It's less than, and a third is 1/3, and that is equivalent to 0.33 repeating. Okay, so the less than means it's our step 1 here that we don't have to redo down here again, but it's our H0 and HA. And because we're talking about a fraction and percentages, we're talking about proportions. And qualitative data, right? Qualitative meaning I'm giving like a yes, no answer, or I'm choosing categories and I'm looking at percentages. So they think they want to test that it's less than 1/3. So that means our HO is equal to 1/3. So part B says verify the requirements to conduct a hypothesis test are met. And it says recall there are about 210 million adult Americans. So our first requirement, which you can find, so we're using page 301 in our formula packet. And you can see the requirements to conduct and test are right here. So we can use those. These are what we worked on in chapter 7. Okay. So random sample. And they did do that. It says random adult Americans. So check. And then we need to check for independence because once they've asked an adult the question, they can no longer ask them again. So that is sampling without replacement. So that means we have to make sure that our sample is less than 5% of the population. And our sample is 3,930 people, is definitely less than 5% of 210 million. So that's a check. Again, you need to show me these numbers. You might not always know the big N, but you'll know the sample size. And then our test for normality, to be normally distributed with proportions, we have to show that N times P times Q, or it's sometimes written as N times P times 1 minus P, right? And this is going to be P0. Okay, that's important to note too. So we're using the 1/3. Has to be greater than 10. So 3,930 times 1/3 times 1 minus 1/3. Okay, so we're using the P0, not the P hat. Is equal to 873.3, and that's definitely greater than 10. So we give that a check. Okay. Step C, part C says, test the researcher's claim at a 0.01 level of significance. Well, we've already done step 1 up here. So step 2 is alpha is 0.01. Step 3 is our test statistic, which remember is just a fancy Z-score. And because we're using page 302, it's a Z0, and this is the formula that you should state for me. P hat minus P0 over I'm just going to draw my picture, and it's a less than, so we're going to be shading over here. And again, we will do the classical method and the p-value method. So I'm just getting it all set up. So let's put in our p-hat. Our p-hat is what they got from the sample. So when they surveyed those people, they said about, they said 30% reported owning a gun. So this is 0.3 minus the 1/3, which is 0.333 repeating. So if you put this in Desmos, if you use 0.33 versus 1/3, it'll just be a slightly different value, and it should still be fine. So the 0.33 times 1 minus 0.33 over the 3,930. Okay. Now I'm going to show you what this looks like in Desmos. So we're using the proportions calculation. And excuse me, we're going to enter in our 3,930 for our sample size. Our sample proportion is 0.3. Our P0, if you put in 1/3, that's fine, because look, it calculates the decimal for us, which is great. There's our test statistic, a negative 4.43. It's very far from the center. So we can assume that our p-value is going to be very small, because it's see on the graph here, it's way out here to the left. Our alpha we're using is 0.01. And because it's a left-tailed test, we're clicking on the less than. Notice that this is the one we're clicking on here. And then it gives us our p-value, which is very small, 0.000047. So there's 5 zeros, 0.000047. Again, that's what it looked like. Okay, so going back to our paper to finish up our conclusion. So the p-value is, yes, very small. So we do reject H0. In the classical method, because it's a less than, a left-tailed, we would be using this. So reject H0 if Z0 is less than Z alpha. And Z0 is a negative 4.43. And Z of 0.01 from our formula sheet is at the bottom of our page here. 0.01 is 2.326. There's our 0.1, 2.326. And it's the negative because it's over here, 2.326. And yes, that is definitely less than. It's definitely in the danger zone. And we are right here. We are way out here. So our conclusion is there is sufficient evidence to support the claim that less than 1/3 of Americans own a gun. I hope this supports you in your understanding of Chapter 9. Please don't hesitate to reach out if you have any questions. Have a great day.